Hello, folks. I wanted to talk to you in a video about the unit circle as it's foundational to the material covered in the class. I have posted some old practice tests so you can look to see what I'm looking for on the tests. And I mentioned in the question and answer on the discussion board, you're going to have to fill out the blank unit circle on pretty much every test. So I wanted to go over a little bit about the unit circle and some mnemonics about how to remember the information on it here. So first off, the unit circle. If you'll notice on most tests, I actually ask you to define it. This is a circle centered at 0, 0, the origin, with a radius of 1. And what a lot of trigonometry is about is studying x and y coordinates of the points on the circle, right? So you might have noticed that the sine function spits out the y coordinate of a particular location on the circle. And the cosine spits out the x coordinate of a particular location on a circle. And the circle that we're dealing with is the unit circle. And the other thing that is other definition worth noting here is that of a radian. A radian is a unit of measuring length or distance that is equal to the radius of whatever circle we are talking about at the time. So as long as we're dealing with the unit circle, the radius is going to be 1. A radian is 1 unit long. So the amazing thing about that, if I have different circles, so this is 1 radian in that circle. Pretend these are circles and that my drawing abilities are actually worthy. This is a radian in another circle. This is the length of a radian in yet another circle. No matter what circle, if I have a piece of string that's 1 radian long, equal to the radius of that circle, it'll take 3.14, in other words, pi pieces of string to lay around the top half of the circle. When we abbreviate that by pi, 3.1415926, pi radians around the top of the of any circle. Okay, so when we specify an angle in radians, what that is effectively doing is actually specifying a distance to travel around the perimeter of the circle. And when you travel that distance, you end up somewhere. And then we look at the x and y coordinates, either the cosine or the sine of that particular location. And the way we measure angles is from standard position, which is the positive x-axis. If we travel in this direction, it's a positive angle. If we travel in that direction, it's a negative angle. Okay, so with that, I'm trying to make this video as brief as possible. I don't want to make it too long, but I also want to cover everything. With all that in mind, let's look at how some of the x and y coordinates on the unit circle were derived. And I want to start off that by looking at a 45-degree triangle, which means if I have a right triangle with one angle 45 degrees, the other angle has to be 45 degrees. And that's an isosceles triangle. The other angle, both angles have to be 45 if one of them is 45, because the angles in a triangle add up to 180 degrees. 45 plus our 90-degree angle is 135, and 180 minus 135 gives us the other angle as being 45 degrees as well. And you may pretend that this triangle is embedded in the unit circle, and we're trying to find out the x and y coordinates of this point here, which is the length of that side and the length of that side. And because we're embedding this in the unit circle, the hypotenuse, which is a radius of the circle, here's the origin, the hypotenuse of our triangle is 1. So we know that, and because this is an isosceles triangle, we actually know that both sides are the same, because isosceles triangles have equal sides and equal angles. So we could write out a little Pythagorean theorem here and solve for the length of the sides. Rationalize the denominator. And this matches what you would see at a 45-degree angle up here for the x and y coordinates, because they're both the same. So the length of this side is root 2 over 2, and the length of this side is root 2 over 2. Okay. Let's see here. Let's talk about the 30-degree angles that are on here and the 60-degree angles that are on here. Again, you're not going to have to reproduce deriving these. By the way, I'll note on the test, again, look at the old tests. But this is an aid to help you understand and remember the information. Okay, so now let's look at a 30, 60, 90 triangle. So we have a 30-degree angle here, 90-degree angle. This angle has to be 60 because they have to add up to a 180. Again, you can envision this as being embedded in a unit circle. That looks more like a 45-degree angle. I apologize, but so we want to find the x and y coordinates of this, which again are equivalent to these side lengths. So how could we do that? Well, so someone noticed thousands of years ago. A lot of the information in this class is many, many thousands of years old. That if I have a 30-degree right triangle, the length of the opposite side is always half the length of the hypotenuse. And the adjacent side is always the length of the opposite side times the square root of 3. And so some examples, if I have if the hypotenuse is 4, the opposite side would be 2, and the adjacent side would be 2 root 3. So on our triangle, because it's embedded in the unit circle, the hypotenuse is 1, meaning that the opposite side has to be half that, and that the bottom side, the adjacent side, is 1/2 root 3, or root 3 over 2, in other words. Now, I know that the hypotenuse of our triangle embedded in the unit circle is 1. And I could use this information that someone noticed many thousands of years ago to deduce those other sides. So just to kind of reiterate, scribes, people measuring land, people trying to measure land to collect taxes, someone had so much time on their hands, they measured a zillion triangles. And they noticed that when there was a 30-degree angle in a right triangle, that the opposite side was always half of the hypotenuse, right? So that's an empirical fact that's been measured, and we could use that to derive the x and y coordinates of our point on the unit circle here. So our x coordinate is root 3 over 2, and the y coordinate is 1/2, which matches what we've got here. For the 60-degree angle, well, you can envision turning that 30-degree angle triangle on its side. So the side, let's see here, the side opposite the 30-degree angle is half of the hypotenuse. The side opposite the 30-degree angle is half the hypotenuse, and the side opposite the 60-degree angle is the length of the opposite side times root 3. So again, if we have a 60-degree angle triangle embedded in the unit circle, our hypotenuse is 1. So I now need to solve for x. Now that we know that our hypotenuse on our triangle that's actually embedded in the circle is 1, 1 equals 2x, x equals 1/2. So that's the length of this side. And now 1/2 root 3, or root 3 over 2, is the length of the vertical side. So we get for our coordinates 1/2 root 3 over 2, and that matches what we've got here. Okay, so the rest of these coordinates are, I only have the first quadrant, Q1, memorized. And then I reflect and use symmetry to remember the other quadrants. So let me go over one other mnemonic here about remembering the coordinates of the angles in quadrant 1. So I'm going to rewrite these kind of above them and fill them in and talk about a mnemonic to remember them. So if you notice, all the denominators are 2. And then for the x-coordinate for these angles in quadrant 1, the numerators are 1, 2, 3 for the x-coordinates. And then for the y-coordinates, it's 3, 2, 1. And then you slap a square root on all the numerators. Now, typically, we don't write the square root of 1 as the square root of 1 because the square root of 1 is 1, because 1 times 1 is 1. So we just write it like that. So that's a mnemonic to help you actually remember the coordinates. And then lastly, it's helpful when you're remembering this stuff, it's helpful to draw a unit circle, put in the common angle. Sorry for the really crappy drawing, right? But if I have an angle, so this one in the middle is 45, this guy's 30, this guy's 60. If I want to know what this angle here is, I could trace the line back to quadrant 1, grab the coordinates there, and use the same coordinates. Note that these and these are the same, but adjust them to be appropriate for the signage of coordinates in quadrant 3. Quadrant 3 is negative x and negative y coordinates, so both of these are negative. And you could do that for all the other angles in there. Okay, I'm going to stop, keep this short and sweet. Let me know if you guys have any questions, and I hope you guys have a good weekend.